In this video, we're going to look at chemical bonds, and these are bonds that hold atoms together. You need to know the definition of a chemical bond. A chemical bond is a mutual attraction between two atoms resulting from the simultaneous attraction between their nuclei and outer electrons. Note that the energy of the combined atoms is lower than that of the individual atoms, resulting in more stability. I'm going to be referring to the graph in a moment. There's a graph that you need to know that goes with this. The three types of chemical bonds that you need to know of are the metallic bond, the ionic bond, and the covalent bond. The metallic bond you dealt with last year, so I'm not going to go into that. You must just know that it is a bond between metal atoms where we have the positive kernels, which is the nucleus and the core electrons, and then the delocalized valence electrons are free to move through the metal, and that is why metals can conduct electricity and heat so easily. The second type of bond is between metals and non-metals. That is the ionic bond. When a metal bonds to a non-metal, a transfer of electrons takes place from the metal to the non-metal. This results in a positive metal ion, which a positive ion is called a cation, and a negative non-metal ion, which is an anion. Positive ions are called cations. Think of cats, they're positive, and anions are negative. That's spelled almost the same as onions, and onions make one cry, so they're negative. These oppositely charged ions are then attracted to each other, forming a crystal lattice in the solid phase. Many of these ionic substances are soluble in water. So I'm going to look at the formation of magnesium chloride. Magnesium is a metal, chlorine is a non-metal. Magnesium is in group 2, so it has 2 valence electrons. That's your metal. The non-metal is chlorine, it is in group 7. So each chlorine atom has 7 valence electrons. So I've drawn the chlorine valence electrons as crosses, and you can see if each chlorine atom could just get one more electron, it would be stable, because then it would obey the octet rule. There would be 8 electrons around each chlorine atom. But then each chlorine atom gains an electron, so it ends up with a negative charge, because electrons are negative. The magnesium will be losing 2 electrons, so the magnesium will end up with a positive 2 charge. So here is my cation, and 2 negative chloride ions form. Those are anions. Take note that your total charge, your overall charge, is going to be 0, because it is plus 2 and 2 times negative 1. Quickly going to go through why magnesium becomes plus 2 and the chloride ion becomes negative 1. Magnesium atoms have 12 protons and 12 electrons when they are neutral. So that's the situation. But now the magnesium still has 12 protons, but it's lost 2 electrons. So the magnesium, when it forms the cation, your magnesium has 12 protons. It had 12 electrons, but now it's got 10 electrons. So it has a plus 2 charge. Chlorine atoms have got 17 protons. The number of protons make it chlorine, and the number of protons here make it magnesium. So your protons don't change. But each chlorine had 17 electrons as well. But each chlorine gains another electron, so each one has 18 electrons. So this has a positive, this has the chlorine now becomes a chloride ion with a negative 1 charge. The magnesium becomes a magnesium ion with a positive 2 charge. So plus 2 times negative 1 gives you a total charge of 0. So the magnesium is 2 plus. Your 2 chloride ions are negative 1. We don't write the 1. So that is why your ratio of magnesium to chlorine is 1 to 2. And this is the formula for magnesium chloride. Remember, this is an ionic substance. It's not covalent, so it's not a molecule. So chlorine, when it is neutral, we call it chlorine, but when it forms an ion, the name ends with chloride. Please take note, ionic bonds do not form molecules. The third type of chemical bond that I'm going to look at in a lot of detail is the covalent bond. So in this video, I'm just going to do the basics, just a few diatomic molecules, and then in the following videos, I will deal more with more complicated molecules. So covalent bonds are between nonmetals and nonmetals. They don't have to be two different nonmetals. They can be the same nonmetals, like, for example, a hydrogen atom to a hydrogen atom. The definition of a covalent bond, you have to know this. It is the sharing of electrons between two atoms to form a molecule. Covalent bonds result in the formation of molecules, and covalent bonds are also called intramolecular bonds inside the molecule. They bond the atoms together to form the molecule. So it's intramolecular bonds. Don't confuse this with intermolecular forces, which is a section you're still going to do. The definition of a molecule is a group of two or more atoms covalently bonded and that function as a unit. So covalent bonds is the sharing of electrons between two atoms to form a molecule. So these electrons that are going to be shared are unpaired electrons from each atom so that they can form pairs, and that way it will be more stable. This graph is important. It is the graph of potential energy versus distance between the nuclei for two approaching hydrogen atoms. So on your vertical axis, we have potential energy. It's normally given in kilojoules per mole versus distance between the nuclei. So this axis is distance between the nuclei, and these distances are extremely small. So they are in picometers. A picometer is 10 to the negative 12. It is extremely small. So when I talk about two hydrogen atoms, the distance between the centers of the two nuclei is about 45 picometers. So if you say 45 times 10 to the negative 12 meters, that is how small this distance is between the centers of the nuclei. So the vertical axis is the potential energy, horizontal axis is the distance between the nuclei. So the best way to interpret this graph is to start from the right-hand side, where your two hydrogen atoms are infinitely far apart. So there's my infinite sign. The distance between these two atoms is infinitely far apart. So that is the situation where we have zero potential energy. So here's your potential energy graph, your axis. They have zero potential energy between them because there's no attraction and there's no repulsion between the two hydrogen atoms. So those two blue blobs are my two hydrogen atoms. They are infinitely far apart, so this is an infinite distance between them. It's far. So there's no potential difference between them. Now they come closer and closer together, so the energy drops. Why does that happen? Here's your energy axis. So the energy is dropping. So energy axis is the vertical axis, your energy is coming down. Why is that happening? That is because the nucleus of the one is attracting the electron of the other one, and the nucleus of this one is attracting the electron of that one. So the distance between the nuclei is decreasing, so the attraction starts to happen now. So they come closer and closer and closer together. So we're reading from right to left. The distance between the nuclei is decreasing. So at this stage, here where your graph is at the lowest point, the energy is the lowest. That's where your molecule forms. So your molecule has formed here, your hydrogen molecule, your H2 molecules, because we're working with the hydrogen atoms here. So this is your H2 molecule. This is very stable, and this is where you're going to have the lowest energy between the two atoms. Then if we make the distance between the nuclei even less, now the two positive nuclei are repelling and the two electrons are repelling. This is a very unstable situation. They want to go back to this position. So if you force them even closer together, the bond distance between the two nuclei becomes less and less. So if you force them closer together, this energy shoots up because it's an unstable situation. At this point, we can read off two things. We can read off the bond length, this value, because remember this is the distance between the nuclei. They will give you this value on the graph and you would have to read it off. This is the distance between the nuclei when your molecule has formed. That is called the bond length. So for the hydrogen molecule, it's about 45 picometers, if I remember correctly. The bond energy will be a negative value, so it's in the order of negative 400 and something kilojoules per mole. So if you add this amount of energy, you get back to zero. So you are breaking the bond between those two atoms so that they can be at this point again where they're infinitely far apart. So if you push them even closer together, this energy is going to shoot up. It's going to be very unstable. They don't want to be too close together. So you can read off the bond length on the x-axis, and you can read off the bond energy on the vertical axis. Note that the energy of the combined atoms is lower, this energy is lower than that of the individual atoms, resulting in more stability. So that means that this energy here, combined atoms with the molecule forming the molecule, is lower than that of your individual atoms because it's more stable over here. Now we're going to talk about the periodic table a little bit because it's good to understand a few things on your periodic table before we carry on with Lewis structures, etc. So your periodic table, here's our key. We're going to be interested in a few of these values. I'm interested in the atomic number, the mass number. It says approximately relative atomic mass. I'm just going to refer to it as the mass number or atomic mass. And the electronegativity I've highlighted. That's the number on the side. The other highlights that I have are the non-metals. So everything that is highlighted in yellow is non-metal. We'll talk about that later. So I'm going to speak about these groups. Group 1, Group 2. I'm skipping the transition elements or transition metals. Here's Group 3, Group 4, Group 5, Group 6, Group 7, Group 8, or Group 0. The group number in green, the group number corresponds with the number of valence electrons, which are the electrons in the highest energy level of the atom. So if I look at oxygen, for example, oxygen is in group 6. I'm looking at the Roman numerals. Oxygen is in group 6, so I know immediately oxygen has got 6 valence electrons. Then the valence electrons are the electrons that are involved in bonding, and we will not be paying attention to these transition elements or transition metals. So let's go back to oxygen. Oxygen has an atomic number of 8. That is the number of protons in the oxygen atom. So if the oxygen atom is a neutral, I must have 8 electrons as well. But I've just said it's in group 6, so there's 6 valence electrons. So 2 of those 8 electrons are close to the nucleus. They are core electrons. The other 6 are in the highest energy level, and they are the valence electrons. So here are the few terms that I've been referring to. Atomic number for oxygen. The atomic number was 8. It's your atomic number. That is the number of protons in the nucleus. The mass number, the bigger number, in oxygen's case it is 16. This indicates the number of protons and neutrons in the nucleus. So if there are 8 protons and the mass number is 16, that means there are 8 neutrons as well, because 16 minus 8 is 8. A neutral atom will have the same number of protons as electrons. So oxygen has 8 protons, so it will have 8 electrons. oxygen is in group 6. So of those 8 electrons, 6 are valence electrons. So 6 of oxygen's electrons are available for bonding. So you can assume that the atomic number, which is your number of protons, will give the number of electrons as well if the atom is neutral. If it is neutral, the number of protons equals number of electrons. Then the number, the electronegativity, that is the number that I highlighted. It's the one on the side. Electronegativity is the tendency of an atom to attract a shared electron pair to itself. So I'm going to compare two elements here. Fluorine has the greatest electronegativity. Here's fluorine with an electronegativity of 4. It is the only element that has an electronegativity of 4. That is the highest electronegativity. So fluorine attracts a shared electron pair very strongly. I'm going to look at boron, number 5. Boron has an electronegativity of 2. So comparing these two, boron and fluorine, boron has an electronegativity of 2, fluorine has an electronegativity of 4. So fluorine is going to attract a shared electron pair a lot stronger than boron. Let's have a quick look at boron. If boron was neutral, it has 5 protons, therefore it will have 5 electrons. 11 is the number of protons and neutrons. So 11 minus 5 is 6, so boron has 6 neutrons. We are actually only interested in the electrons. So it's got 5 protons, so it will have 5 electrons if it is a neutral atom. Now we're going to look at our first actual covalent bonds. These 4 are mentioned in your guidelines. Hydrogen, fluorine, oxygen, and nitrogen. Why do they form diatomic molecules? There are actually 7 diatomic molecules: hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. But fluorine, chlorine, bromine, and iodine, these 4, are all in group 7. They are halogens. So they're all going to have the same outer electron structure. So we only need to do fluorine, then we will know how these other 3 form diatomic molecules as well. So I've done a table with hydrogen, nitrogen, oxygen, and fluorine, not necessarily in that order. So here's our table, your molecule, the Aufbau diagrams for both of the 2 atoms, the Lewis structure, and the Cooper structure. So the first one, the simplest one we're going to look at is hydrogen. If you have a periodic table with you, hydrogen has an atomic number of 1. So hydrogen has 1 electron. There's my 1 electron in the 1s orbital. So here's my 1 hydrogen atom's electron. There's my other hydrogen atom with its electron. When you're going to show that they're going to combine and the orbitals are going to overlap, have one spinning up and the other one spinning down. There's a reason why they must go in opposite directions. I'm not going to go into that now. So I've made this one in my Lewis diagram. I've made this one a cross and that one a dot, or vice versa. So there's my Lewis diagram. There's the cross from the one, the dot from the other. So this is a single covalent bond. There's your Cooper structure, where you just show a line. So this is Lewis, and that is Cooper. The next one I'm going to look at is fluorine. So again, if you have a periodic table, fluorine has got 7 valence electrons. Fluorine is in group 7. There's your 1 fluorine electron structure. There's your other fluorine electron structure. So fluorine has 9 electrons in total. It's 9 on the periodic table. The atomic number is 9. So I've got 2, 4, 5, 6, 7, 8, 9. Remember the p orbitals go 1, 1, 1, and then you go back again. So fluorine atoms have one unpaired electron, and this fluorine atom has one unpaired electron. This is a very unstable situation, so these orbitals overlap. The Lewis structure looks like this. Crosses for the one, dots for the other. You don't have to do that. You can make them all dots or all crosses. There's one pair of electrons that is shared, so the Cooper structure looks like this. It's a single covalent bond. Some of your teachers are going to want you to put those pairs that are not bonding around these fluorine atoms in the Cooper structure. So you must please do what your teachers do. I haven't put these pairs of electrons that don't bond. They are called lone pairs. I haven't put the lone pairs in here, but if your teacher wants you to do that, you must please do it. So fluorine has the same structure as chlorine, bromine, and iodine because they're all in group 7. They will all have single covalent bonds. The oxygen diatomic molecule. Here's our one oxygen, and there's our other oxygen. Oxygen has 8 electrons in total. Oxygen is in group 6, so it has 6 valence electrons. So these electrons in the 1s orbital are not valence electrons. They are core electrons. They are not involved in bonding. So in our Lewis diagram, we only show these 2 lone pairs and the 2 unpaired electrons for each atom. So there are my 2 lone pairs. There are my 2 unpaired electrons for each atom. Lone pairs, unpaired. So the unpaired electrons are going to share, their orbitals are going to overlap, they're going to share a space. These are the bonding pairs, and those are the lone pairs. So your Lewis diagram for oxygen, diatomic oxygen looks like that, and the Cooper structure for the oxygen molecule looks like this. Then we're going to look at nitrogen. Nitrogen is in group 5, so there should be 5 valence electrons. Nitrogen has 7 electrons in total. So the electrons in the 1s orbitals are not going to take part in bonding. Those are core electrons. So the 2 nitrogen atoms have got 2, 3, 4, 5 valence electrons. 5 in this nitrogen atom as well. A lone pair and 3 unpaired electrons. So there's your lone pair, the 3 unpaired electrons. So the sharing, you guys should be used to this by now. Those share, take note, I'm not drawing arrows, and those orbitals overlap. So you have 3 pairs of bonding electrons with 1 lone pair still on each nitrogen atom. So the Cooper structure, you just draw the 3 lines. Again, if your teacher wants, just draw the 3 lines. Just remember, if your teacher wants the lone pairs in, you add them in. So this is a triple covalent bond. Oxygen diatomic molecules have a double covalent bond. Fluorine and hydrogen have single covalent bonds, and the chlorine, bromine, and iodine will also have single covalent bonds. So chlorine, bromine, and iodine have the same outer electron structure as fluorine, as they are all in group 7, they are halogens. They all have 7 valence electrons. They will all have a single covalent bond that forms the molecule. Electronegativity differences in each of these examples that we've done, all 4 examples, the electronegativity difference is 0. We write electronegativity difference in shorthand like this. Whatever abbreviation your teacher uses, you must use. If your teacher's not happy with this, then you use the abbreviation that your teacher says, because writing electronegativity difference is quite a lot to write. So they often come up with abbreviations. The shared electron pairs in these 4 examples are therefore attracted equally to each of the atoms in the molecule. The resulting covalent bonds are therefore pure covalent bonds because the shared electron pairs are attracted equally to each of the 2 atoms in the molecule. There isn't an atom in the molecule that is pulling the shared electron pair more than the other one. Then 2 more definitions that you need to know for this chapter. A bonding pair is a pair of electrons that is shared between two atoms in a covalent bond. And a lone pair is a pair of electrons in the valence shell of an electron that is not shared with another atom. So if we go back to our table, here are the bonding pairs in the nitrogen molecule, and that is a lone pair.